You're live.
All right, are we back?
Might want to wait for people to get back in the room.
Definitely wait.
Okay, we got back at some technical difficulties. Some things. I think I'll wait a little bit for people to get back into the room. Right, are we back?
Yep.
Very good. Okay, the question is, I wasn't really sure where we were, and good, I'm back. I'm going to wait a little bit here, and I kind of felt bad about jumping around on the with all that stuff, and I think I'll try to pick up where we ended, because I was doing the different. I'm going to wait here for a little bit for more people to get back. Hopefully they can find it. I had to restart the stream. Some of the settings got off, and I have a brand new stream. Hopefully everyone is starting to come back. Oh, good. This is really good to see everyone coming back now. Okay. I did close out what I had before, so I'll have to kind of open it up again, but that's okay. We will do this tonight. We will get through this for sure tonight. Let me pull up the lecture. Okay, here we go. Yes, okay. Okay, we're coming back. Let's go back, and I'll go back to example number 2, where we were before, right here. And I need to bring this back, Excel back, and set it up again. So the set it up quickly. T, C, this is the values. This is the objective function. And this is such that we have wood, whoops, and then labor. This is 30 and 20, and this is, what is this? 5 and 10, and this is 300, 110. The objective is so we had 45 and 34. $45 and $34, and this is going to equal, I'll do the sum product of these two and these two minus 390. There we go. Okay. So we're there. There. We're back where we were before. Let's go ahead and box this in so we can keep things straight, okay? And then when we solve this thing, set this up again. There's the objective function we want to maximize. When you change our decision variables with these are going to be less than or equal to these over here. Okay. Make it the simplex algorithm, say solve, and I did it wrong. Did it fast and I did it wrong. Max, and these are those. Oh, I gotta take this down here. Close this out. Yeah, I didn't have any constraints. You gotta have constraints. Let me just copy this down. There we go. There we go. And now I got the constraints. This will do it. Up. And we don't want that. And we don't want that. There we go. Now we can solve it. And then we'll have it. There we go. That's where we ended. Now we're back to where we need to be. Okay. So be careful when I start moving things around here. I've got a lot of things open and I mess things up. All right. So okay. Yeah, I think I have. I'm wondering if I have everyone here. Yeah, I think I do. Okay, going on. That was the realistic. Going to modification number 2. It's kind of unfortunate that we had that interruption. Okay, where were we? Oh yeah, modification number 2. I want to increase the cost by 50 cents an hour. If you are, I'm not really sure. I have a lot of things open here. If you're listening to this, if you could just say that I'm live and you're here with me.
I think the chat, you have the wrong chat open. Close out that chat. And then reopen the chat from there. See, there it is.
This is the right one?
Yeah. Gotcha. There you go.
Okay, we are back. There we go. I had the wrong chat open. Thanks, guys. We're getting there. All right, let's go now. Okay, let's get some good stuff. Now we've lost maybe 10, 20 minutes. I will try to just focus to get through this because this will be recorded. Modification number 2, and this will be a second video. This will be video number 2. I won't try to merge them. I'll keep them separate. Okay. So example 2, wood is a fixed cost. We had wood as a fixed cost, and so we have unit cost of wood, and the variable cost is labor. If we use labor, we pay for it, and then we have our prices here. So then we have our variable profit within our objective function here, and that's going to be the equation of our objective function. Now, when we increase the cost, the variable cost by 50 cents an hour, it went from 640 to 690. I'll take the 690 and put it in here, and the 45 and 34 then are changed to 42, 50, and 29. I solve it, and I'll come up with 41. And I was going to do this here, like 42, 5, and 29. Whoops, see, I grabbed the wrong one. Okay. Let me do this. There we go. If this is 42.5, and then this is going to be 29, okay, and then we solve it. It's going to give us 41. Okay, and so the idea here is that the second one, modification number 2, if I increase this by 50 cents an hour, it'll change my coefficients. And when you solve it, then the profitability will drop from 96 down to 41. That's a $55 decrease. Okay. Yeah, sorry about that. I pulled the wrong thing in, guys. That's a mirror on mirror kind of thing. So you had a $55 decrease. So the idea here is cause and effect. In other words, if you're going to change the cost of labor, that's a cause. What's going to be the result of that? What's going to happen then? What kinds of things are you going to see within your operations, within your business? Well, what you're going to see is the profitability is going to drop by $55. So you think, well, if I increase the labor cost, I'm going to have lower profitability. You know that, but this says, well, how much lower? Good question. Well, if this goes 50 cents, then this drops by $55. So a 50-cent increase of my labor, my profitability, if I'm making 4 tables and 9 chairs, will drop to 41. For every 50-cent increase, I have a $55 decrease. So this is a cause and effect. So what linear programming will do, if you have everything connected, it'll say, with this, if you make these changes, this is what's going to happen within your operations. And so you can actually document it, you can have sensitivity analysis, and actually have numbers to help you make informed decisions. If I increase this, modification 3, if I increase this by another 50 cents, from 640 to 690 to 740, and I take the 740, I put it in here, and I get new values here for my variable profit, I get 40 and 24, I solve it again. So the argument here is as well, every 50-cent increase of labor, my profit decreases by $55, went from 96 down to 41. But if that's true, if this goes down another $55, I'll be operating at a loss. But when I solve this, I get a positive $10 because what happens is it finds the optimal solution by changing my product mix, my production changes. And so the idea here, the takeaway, which is extremely important, it's simple, but it's very important in business, is that when your cost starts changing, there's going to be an effect, cause and effect. And so your profit decreases. Well, eventually, it's going to be negative unless you change your production mix, or you change your production plan, or you change how you produce things. And so this is being responsive to changes in the demand, being responsive to changes in your cost structure, in the cost of your resources, in your revenue. It's being responsive, and it's changing your operations to respond to those changes. And this modification 3 will not only tell you need to be responsive, but what to change to. And so this is responsive analysis. And so responsive analysis, oh, in order for me to stay profitable, I have to change my production mix. We say, wow, making 0 chairs, well, yeah, I'm making 0 chairs if you want to stay profitable. I don't want to make 0 chairs, fine. Make 9 tables and 1 chair, or something close to that. But you have to get away from 4 tables and 9 chairs if you don't want to be negative. So this will tell you what to change to. And then if I change this, modification 4, if I change this another 50 cents per hour, then it goes up. The cost is so great that no matter what you do, you're operating at a loss. But what this will do is minimize those losses. And sometimes you'll operate a loss. Hopefully, the profitability will come back, and you'll minimize those losses for a while until you can come back in whatever reason you have to be negative. So each of these modifications have an application. One, simplistic to more realistic. The other, what are cause and effects to changes in your operations. 3, be responsive to market changes, to cost structures, to revenue changes. Be responsive and change responsively. And if you don't, sometimes it's referred to as mismanagement, being non-responsive. We've always done it that way. We have to change with the times. And 4th is minimize your losses when you have to operate at a loss. And sometimes you have to get out, okay? So these are 4 very good applications of the modifications, and there's a lot more. That's why linear program is so popular. So let's go on. So the second, example 3 modification, let's go back to the redwood furniture problem, the original. Craig, yes, you're still maximizing, you're minimizing your loss, you're still maximizing your profit. So a minus 15 is the maximum profit you can have, which means you're losing $15. Okay, and if it was 4 tables and 9 chairs, let's bring this back, you'll be losing a lot more. Okay, if we take this and say 37, let's take these two. Got to be careful here. Put him back in here, and then it's minus $69. Okay, 69. Well, what LP will say, well, instead of 4 tables and 9 chairs, if you want to maximize your profit, is minimizing your loss, then you would make 10 tables and 0 chairs, and the minimum loss, the maximum profit minimum loss would be $15, not $69. That's the idea. Okay, increase your wood capacity. This is a good one. Again, I'll try to just go right through it and not take too long tonight. Okay, consider the redwood furniture problem where the wood capacity is increased from 300 to 900. Now notice in example 2, we changed the monetary structure. Now we changed the profitability down here. In example 3, we're changing capacity. I'm going from 300, I'm going over here to 900. Well, so the 900, I just changed that one number. Well, for 300, here's the solution for 300. The optimal solution is 4 tables and 9 chairs. But if this increases to 900, here's my wood constraint. This is dotted one, is my old one. My new one is this is my wood constraint right here. And the solution then is going to be right here, 22 tables and 0 chairs. So again, I'm zeroing out my chairs. I'm sure just zeroing out chairs a lot. Why? There's a good reason. Let's back up to example 2. Why would chairs go to 0? I think we mentioned this at one time earlier, I think in the last video. But right here, I'm changing cost. I'm changing cost of labor. So for labor, which one is going to have the greatest impact when you change the cost of labor? Well, the greatest impact is going to be chairs. So if the cost goes up, the greatest impact is going to be on chairs. The weight is going to be chairs. So chairs are labor intensive because you have more labor in chairs than you do tables. So if you're increasing the cost of labor, it's going to affect chairs in a much greater fashion. And you can see that because it went to 0. And also, so the here, chairs then is referred to as labor intensive. So if you help labor or if you have greater cost of labor, you'll hurt the chairs, not the tables. The table productivity goes up, the chair productivity goes down. Likewise for wood, tables is wood intensive. If the wood cost goes up, the tables will go down and the chair's productivity will go up. And so these will also tell you the wood intensive and labor intensive for tables and chairs. Okay. And this is a really simple example, but the way you do it is change a resource and see what happens with a relative difference. And there's where the sensitivity analysis comes in. We'll get into that not this week. Okay, now let's go from profitability, let's go to capacity. So now we go to 22.0. We went from 4.9 up here to 22.0 for this, the old one, and then this is the new one. Okay, now I'm using this as an example to introduce some more terminology. First of all, decision variables. Decision variables are called basic variables if the value of the variable is positive. For example, t is positive, so t is a basic variable, just a term. A non-basic variable, if a variable is non-basic, the value will be 0. Well, c here is non-basic because it has a value of 0. If it has a value of 0, if it's non-basic, it'll be 0. So this is basic, this is non-basic. So that's just terminology. It's all it is. Okay. Now for constraints. Now the binding constraint. Notice the optimal solution here, which is 22.0, is right here, and it's on the boundary of the wood constraint. So the wood is called a binding constraint because it's on the boundary. But if that point, 22.0, is on the boundary of the constraint, then it's on the line. But if it's on the line, then equality holds. If equality holds, then the left-hand side equals the right-hand side. In other words, if I take 22.0, I go to the wood constraint, 22 times 30 plus 0 times 20 is 660. Okay, and so oh man, this should be right here. 22.0, not 30.0. So oh boy, I'll change that in my notes when I go back and change that. The arrow should be there. So it's the labor constraint that's binding. The wood constraint is non-binding, because this 22.0 at 22.0 that point is on the boundary of the labor constraint. So the labor constraint is binding, which means if you take 22.0 multiplied by the coefficients for the labor constraint, the left-hand side equals the right-hand side, and the difference is 0. So the wood constraint is out here. So at this point, it's not on the boundary. So if I take 22.0 in the wood constraint, the left-hand side is 660, the right-hand side is 900. They're not equal. So if what you use equals your capacity, if the left-hand side equals the right-hand side, okay, then that's called a binding constraint because that point is right on the boundary. It's right on the boundary. Okay, and the difference between the right-hand side and left-hand side is called the slack of the constraint. And so slack has a definition of the left-hand side relative to the right-hand side. If the right-hand side is here, the left-hand side value is down here. That difference is slack. Okay, and it's always the left-hand side relative to the right-hand side. Now, if otherwise, it's called a non-binding constraint. Okay, so the labor is binding, but the wood here is non-binding because 22.0 does not lie on the boundary. Okay, now notice I do have two non-negativity constraints here. Okay, so at this point, 22.0, which one of these constraints, the T or the Z, the T or the C, which one of these is going to be binding? Let's do it this way. And so either the T or the Z, which one is it? So let me just say T here. Which one is binding? Well, if T is 22.0, then that does not equal 0. If C is 0, then C is binding and T is non-binding because 22 is not equal to 0. So when the left-hand side equals the right-hand side, it's binding. When they're not equal, it's non-binding. But notice now the left-hand side is greater than the right-hand side, so that's called surplus. When the left-hand side is less than the right-hand side, that's called slack. Okay, and so down here to summarize, the variables, standard form, the left-hand side has the variables. The right-hand side has the constants. Now, when the left-hand side value equals the right-hand side, they're called binding constraints. at a point, whatever that point is. Now, at a point, if the left-hand side does not equal the right-hand side, for a less than constraint, the left-hand side here is less. That difference is called slack. For a greater than constraint, the difference will be called surplus. Okay, and for equality, it doesn't apply because it'll never be not equal because it's constrained to be equality. Okay, as far as graphing, I'll show you how to graph probably next week. That was confusing. So at a point, right here at a point, actually let me do it this way. Let me put two more in here. So let's put the T here, and let's put the C. Okay, so 22, 0, this is 22, and this is 0. The right-hand side is 0 and 0, okay? And so the left-hand side here is, this is 1, and this is 1. This is 22, and this is 0. Okay, so now, and this is going to be greater than or equal to. So there's my non-negativity constraints. So I have 4 constraints here, okay? And there they are, T and C. 1 times T, 1 times C, and 22, 0. Okay, that's the coefficient of T. Coefficient of C is 1 and 1, and 0 and 0. Okay, so when I multiply, this is the left-hand side, this is the right-hand side. So notice the left-hand side. When the left-hand side equals the right-hand side, what's the difference? The difference is 0. And that's called binding constraint. That's a binding constraint. Now, when the left-hand side is lower than the right-hand side, that's called slack, and that is a, non-binding constraint. Okay. Now over here, when you're greater than, the left-hand side is more than the right-hand side. That's called surplus. And that's equals 22 minus 0 equals 22. Okay. And that's referred to as a non-binding. Okay. And then the surplus here is 0 minus 0 equals 0. And that's referred to as a binding constraint. Okay. So when they're equal, it's binding. When they're not equal, it's non-binding. And when it's non-binding less than, the left-hand side will be less than the right-hand side. That difference is slack, because the left-hand side is slack. And here, the right-hand side is 22 more than the left-hand side is 22 more than the right-hand side, so the surplus is 22. Okay, isn't C 018? Nope. These are the coefficients. See, this is your constraint set down here. So 35 and see 10 here, T I mean. The coefficient of T is 1. And the coefficient of C here is 0. That's what the 1, 0 means. That's a coefficient. The right-hand side is 0. And this, the coefficient is 1. See, the coefficient here is 1. Coefficient is 1. 0, 1. Aha! Good point, Craig. That's my next point. You have to be careful. You have to be careful. The word slack and surplus are mathematical terms, not practical terms. For example, if you make 22 tables and 0 chairs, you're making 660 board feet of wood. You have 900, And so the slack is 240 mathematically. But if you've used only 660, but you had 900 to begin with, you have a 240 surplus. That's a common use of the word surplus, not a mathematical use of the word surplus. So you got to be careful with language. Again, language is important. You have a surplus. Oh, so it's a greater than constraint? No, it's a common use of the term surplus. I have surplus wood. Okay, and I have slack wood, which means my constraint, my mathematical value of that constraint is less by 240 than the right-hand side. Okay, so you got to be careful with the language. And by the way, slack and surplus is not my language. That's what came down the pike. Okay, and actually, this is in business and other disciplines. These have different terms. They have different words which I like better. But I'm using this because we're in business. Okay, so this is going to be important because binding constraints are going to be important because if the binding, so what does binding mean for the labor? That means all the labor is being used. What does non-binding mean for wood? All the wood is not being used. Okay, so the binding and non-binding mathematically has very practical interpretations and uses. Okay. Again, notice very quickly in passing, notice as the capacity increases of my wood, it went from 300 over here to 900. As the capacity of my wood increases, which one of these then went up and which one went down? Tables went up, chairs went down. So one goes up and one goes down. And so whereas tables we can see is wood intensive, so the more wood you have, that's going to support the production of tables over chairs because chairs uses less wood. Interesting. So so the idea here, you can change the money, you can change the cost and revenue, and change production. You can also change resources and change production if you're driven by optimality, and a market is driven by maximizing profit. So changing capacity, availability can change productivity. Now, very quickly, see, I can talk a lot about this, but I have a lot more to cover tonight. So if we can do this by changing pricing or cost, or changing availability or capacity of resources, either way, if we can change the attractiveness of products going up or down within a company, can you do the same thing within an industry? Yes. If you can do it within an industry, can you do that within an economy? Yes. If you do that with an economy, a domestic economy, can you do that in a worldwide economy? Absolutely. That's exactly what happened in the 70s and in the late 70s when OPEC nations began changing the capacity of natural resources of fossil fuels. It changes the price and changes the productivity. Okay, because we're driven by profit. So linear programming can have huge models to look at the economy, to look at industries, to even look at global supply chains. Absolutely. And those models do exist. They do exist. Okay, let's go on. Oh, I've given some examples in here. See this exercise 1 and exercise 2, just some examples to go and to make sure that you know how to use this, a max and a min and see, here's a greater than constraint, here's a less than constraint, a quality constraint. Yeah, we're still maximizing profit. Yep, we're still maximizing profit. Now the exercises here, just to get used to Excel, is all it's doing. Okay, Now, and then exercise 2. Now, before we go to the special cases and applications, let's come back to Canvas. Oh, I got to open up Canvas. Got to be careful here. I don't want the same thing to happen. There we go. I was clicking too fast before. Okay, let me bring Canvas back up. 6630. Here we go. Okay, here's home. Now, if you go to the website here, mdharper.com, if you go to my website, Operations Management tab, come down here to linear programming. I have a lot of Excel spreadsheets in here, and these Excel spreadsheets will show you how to, I'm getting ready to go into the product mix, ingredient mix, transportation LPs, okay? And I have a video, and those videos will describe things, will present things. See, I'm kind of, this is a lecture. I'm kind of explaining it and back and forth and answering questions. These videos are presentations, and I urge you to watch them because they present everything, and then I talk about it, and it's two different types of learning, and both of them really is good to go together. But I also give you these Excel files, okay? Now, to download these Excel files, actually they I use this third party. Anyway, right click, and say open link in new window. Gives you a new window, and it downloads it. And here you can open it. Boom. And there it is. Okay. Now notice what I have here. Go ahead and enable editing. Let's back up here to the very beginning. There we go. What I have here in this spreadsheet is not only do I have how to set it up, and you can actually come in here and actually look at the functions. You can see here how I set it up with the sum products and everything. And also here is how you graph it, okay? And also up here, click the graph and come up here the chart design formats, and over here the chart design, over here the elements. You can see exactly my settings. Okay, and you can see how I do things and select the data. You can see how you put data in there, okay? So you can see this, but I also screen captured and put in here the solver parameters that are needed for this, okay? And then when you click solve, it's going to give you this and click OK. So essentially I'm setting it up, graphing it. I'm showing you the solver window, and then the solver result window, okay? Now, what we're not going to do in this course, today, is the sensitivity reports over here. And I'll allude to those maybe next week, okay? But not this week, not today. Then the exercise 1, I do the same thing. Boom. Exercise, here's the max, there's the min. Exercise 2, I do the same thing. There's a max, there's a min. You can make it bigger. And then I start with 3 different special cases: an infeasible, unbounded, multiple solutions, and then 3 applications: a product mix problem, ingredient mix problem, transportation problem. So we're going to be doing 6 applications. So I'm not going to do Excel anymore. I'll do it next week. I'll be working through problems. But I'm not going to do Excel anymore. I'll just be setting it up, looking at the solution, and interpreting it. So let's do it. There we go. So here are the 3 special cases: infeasible, unbounded, and multiple solutions. And here are the applications: product mix, ingredient mix, transportation. Now when I do the applications here, I'm going to focus on the structure of the problem. Well, the structure is the same, but the definition of the matrix, the definitions in here are different. That's how you identify or define the problem, by the structure of the problem and the definitions of the terms within the table. So let's start with the special cases real quick. Okay. Infeasible LP. Scenario. The redwood furniture problem, where the boss comes in and she says, "Oh, before the next production run, I have a special order from a special client. The special client wants 24 tables. So your next production run, make 24 tables, and then when you're done, and then whatever resources are left over, just maximize your profit." Oh, okay. That's a request, a very common request. Special order, maximize profit. So she leaves. And you say, "Oh, I know how to do this. Special order 24. Let me come down here. I'll put an order of 24 in here. T is greater than or equal to 24. There's my special order. Then I want to maximize my profit above that. Fine. Over here, here's 24. But then if it's greater than 24, then I'm going to say everything to the right of this line is greater than 24. And so I have this half space out here. But then my wood and labor is down here. So my feasible region is down here for my wood and labor constraints. My special order is over here on the right. Wait a minute. There's no region of points which satisfy all these inequalities at the same time. So there's no feasible points. If there's no feasible points, there's no extreme points. If there's no extreme points, there's no solution. And this is called an infeasible LP. And so it's possible. A lot of people say, "Oh, well, when will this happen?" Oh, it happens more than you think. Do this much work with this much money. Wait a minute, I don't have enough money. Do this much work, make these many products with this many people. Okay, you have 10 hours to do 40 hours worth of work. How often does that happen? Okay, so this does happen. Okay, and so at this point, I have something really valuable to bring into this lecture in a business course. You look at this mathematically and you see, oh, there's no feasible region because this constraint and these constraints, there's no points which satisfy both of them. So I see that. I see there's no region. I see there's no solution. So the boss comes back and she says, "Why haven't you done anything? Why haven't you done it?" And so you can answer this in two ways. One way is mathematical. And you can say, "Oh, well, the extra constraint, when I put it in the constraint set, there's no feasible region because no points will satisfy all the inequalities at the same time. Since there's no feasible region, there's no extreme points. Since there's no extreme points, there's no solution." And that statement is correct. But is it helpful? Says, "What did you say?" Or a second way you can answer her, it says, "Why haven't you done anything?" You can simply say, "I don't have enough resources to make 24 tables." That statement is correct. Which one is more valuable in business for someone to say, "Oh, then what do we do about it?" Given the mathematical reason why it doesn't work, doesn't really lend itself straightway to a solution. But a very practical answer, "I don't have enough resources to make 24 tables," lends itself to a common comeback. How many resources do you need? That's how we solve this thing. Well, that moves you into a different type of linear program. And that different type of linear programming is called goal programming. The goal now is not optimizing profit. The goal is to make 24 tables. So it's not how much tables and chairs do I make to maximize profit. Now the goal is, how much wood and labor do I need in order to make 24 tables? That's my goal. That's called a goal program. And that goes beyond this course today. I'm not going to get into it. But if anyone wants to do this for the project, this would be a great project. Goal programming is extremely popular in business, especially operations, marketing, in finance, because how many companies have a goal to achieve? Okay. Anyway, say you solve this with goal programming, you come back and you say, oh, here's how much wood, here's how much labor I need to make 24 tables. And she said, okay, well, then how much profit above that are you going to make? Oh, I didn't do that. That's a second goal. She actually gave you two goals. One goal was to make 24 tables. The other goal was to maximize profit. And so then the answer would be, the practical answer, the helpful answer is, solve the goal programming for the 24 tables. Say, here's how much wood and labor I need for 24 tables. Now, above that, I can make as much profit as you want, depending on how much resources you give me. How much profit do you want? Oh, I want above the 24 tables, I want $100 profit. Fine. I can tell you how many resources we need then. So one goal is 24 tables. The other goal above that is $100 profit. These two goals, then we can solve that as two dual goal programming. Well, usually a company has many goals. And so usually multiple goal programming is extremely popular in business. As a matter of fact, knowing goal programming, moving into large organizations where you just don't fly by the seat of your pants, you have to actually do analytics. Goal programming is extremely popular and powerful. Let's go on. Next is an unbounded LP. Suppose for one reason or the other, the less than or equal to, all the constraints were greater than or equal to. Greater than or equal to, greater than or equal to. Suppose that happened. A mistake or whatever, you want more than a mistake was happened, let's say. Well, when that happens then, the feasible region then is in the upper right here, and it goes to infinity. So then when you try to optimize it, then it's going to go to infinity. And there is no solution. But a feasible region does exist, and extreme points exist, because that's an extreme point because it's feasible. That's an extreme point because it's feasible. That's an extreme point because it's feasible. These here are not extreme points because they're not feasible. But no optimal solution exists. So there's a good trivia question. It's kind of like, well, if you have an LP with an extreme point, then you have to have an optimal solution. No, that's not true. Here's an example of 3 extreme points. None of them are optimal because I can find a value out here somewhere that has an objective function which is greater. So they're not optimal. But if you have an optimal solution, then the LP theorem has embedded in it. If you do have an optimal solution to an LP, then it's going to include at least one extreme point. So an extreme point doesn't mean you have an optimal solution. But if you have an optimal solution, it does mean that one or more extreme points are part of that solution. We'll see that in a minute. Well, here is an adequate constraint set. So if these constraints were correct, then you need less than constraints. You have some constraints that are missing. When you try to solve something and it's infinite and it's unbounded, then either you've formulated it correctly and you solved it incorrectly, you've formulated it incorrectly, solved it incorrectly, or you don't have all the constraints in the constraint set. There are some missing. And those are the common causes of that situation. Now, the third special case is multiple solutions. So this is interesting. This is good. This is important. Okay, I'm going back to the redwood furniture problem, but I changed my unit profits. It was 6 and 8. I've changed it to 5 and 10. But the reason I changed it to 5 and 10 is those are the same numbers as the coefficient of my labor constraint. Notice that, 5, 5, 10, 10. Therefore, when I optimize this thing, I'm going to get 2 extreme points that are optimal. And both of these extreme points lie on the labor constraint. So that point is optimal and that point is optimal. Well, infinity only works in theoretical physics. One of these days we can talk about that, about theory, about infinity. Infinity is very interesting because in theoretical mathematics, I have a degree in theoretical mathematics, and you can have infinite series, and you can make anything equal to anything, pretty much. You can formulate infinite series. In infinity, things just kind of, everything equals each other. You can make infinity equal zero. Zero equals, you can do all kinds of crazy stuff in infinity. And so, anyway, that's a different conversation. So here we have two extreme points that are optimal. That extreme point and that extreme point. Every point between the two extreme points, every point or each point is also optimal. So theoretically, we have an infinite number of optimal solutions along that line segment. Okay. Now, when I say infinite, so you can, if we can make 1.2 tables or we can make 3.5 tables and 8.6 chairs, because LP doesn't give you integer solutions. It gives you real numbers, whole numbers. It gives you real values and rational, irrational numbers. Okay, so theoretically, there's an infinite number of solutions between those two extreme points. Some people say, how can you make 1.5 tables? People do that all the time. You make 1.5 tables, you stop, you go home, you come back to the next production run, and you finish that table and move on. Okay, that kind of thing. Anyway, but the thing about multiple solutions is that now sometimes you want to design. Now, here I'm changing my profit. Maybe you want to design your operations, the efficiency and the design of your operations such that you have multiple solutions. Because if a manager has multiple ways of achieving optimality, then they have a lot of flexibility and he has a lot of robust type solutions no matter what is thrown at him. Oh, this cost goes up. Well, I can absorb that and still maximize my profit. Oh, this resource was decreased. I can still absorb that. If I've formulated this correctly, then if I design this correctly, I can absorb that problem to where my profitability is still optimal. You can absorb problems to a point. And so there's where multiple solutions are extremely powerful. Okay. I'll talk about this a little bit more, I think, next week when I do some of the applications, some of the homework problems. Okay, now 3 applications. First, the product mix. A company manufactures heavy-duty and light-duty versions of their table saws. From the following information, how many saws do they produce in their next production run to maximize profit and not exceed departmental capacity? And there, I've given you this structure of the table. Again, remember I mentioned the structure is important to identify what kind of problem it is. Let's back up here. Here we go. The structure of a product mix problem. Where you have products up here, you have profit, and profit could be revenue, return, net present value, could be anything. And over here are your resources that you have to make the product, and these are the capacity or constraints on those resources, and these are production standards. And the standards are always defined as how many resources are needed for each product. That's the definition. Okay, so let's come back to our problem here. Our product mix. Okay, so right here, we have a machining department, assembly department. We have heavy duty and light duty saws, $900, $600. And we only have 2 departments. There's more departments in this, but I'm going to come back to that in a minute. 4,000 hours capacity for these 2 saws, 5,000 hours of capacity for assembling these 2 table saws. Now, people say 4,000, 5,000. Yeah. Well, machining department, assembly department for this company, they make a lot more products than just table saws. They do a lot of stuff. And so it says, okay, it's your turn, table saws. Okay, you only have that many hours. That's it. You can machine it. You can assemble it. Machining's moving on. That's all you have. How many of each do you make to maximize your profit? Okay, and if you don't do that, you're going to spend the same amount of money, the same amount of hours, same amount of people, same amount, and you make less revenue, less profit. Okay, so these kinds of problems are very, very useful in a repetitive fashion. Now, I want to emphasize the structure of the problem. For example, one, recognize that this 2 hours and 1 hour, this is how many hours of this department is needed for each one of those saws. And this is how many hours is needed for each one of those saws. And so notice the heavy saw, the heavy duty version is machine department dependent. The light is assembly department dependent for one reason or the other. And I just kind of picked these numbers just to demonstrate these things. Okay, so there's your capacity. Now this structure is important because you need the structure to define the problem. You need the structure then to move down here to define the problem. But also you need the structure to define the problem. I mean to actually pull out the right values to solve the problem. In other words, rarely in business do these problems come at you this way. You have to identify it. You have to see it. Okay? So you have to see it. For example, I used to be in consulting, and so if you go into a consultant, the reason you're there is they don't know how to do what you know how to do, and so they don't know the right information to give you. And there's a problem there. In school, and usually it's not so much a problem at graduate level, but observe at the undergrad level. They go, I know how to work these problems. You do? Yep, give me a problem. Here's a problem, they work it. But when they're given a problem in a textbook, they're given everything they need to solve that problem. That never happens in business, in real life. If you go into someone and to consult a company, and they say, okay, we want to maximize our profit, and we want to maximize profit on our table saws. Okay, can you do that? He says, yes, I can. Okay, good, fine, thank you. Come back and tell me what we need to do. Wait a minute, I got some questions for you. Okay, how many saws are there? Oh, there's only 2, heavy and light. I thought you knew that. No, I didn't know that. I'm a consultant. I don't work here. You have to give me this information. It says, oh, okay. It says, tell me everything about heavy and light saws. Tell me everything you know about heavy and light saws. So the client goes, oh, okay, sure. Well, the heavy saw, we have that red because it's heavier, and light, we made it blue. So we have red and blue saws. Now the heavy, I wanted to put a green sticker on it. No. No, that's not the kind of information I need. Oh, well, what do you need to know? Well, I need to know the value of them. Oh, well, the heavy is really important to us. We place a lot of value on that because we want the heavy saws because we know the heavy saws are going to be doing heavy work. No, that's not what I mean. That's not what I mean. You have to be very, very specific. But in being specific, you have to ask the right questions. For example, if you make one heavy-duty saw, how much profit are you going to make from that? Now, that's a direct question. You have to ask the questions to get the right information to get to that number, or a number close to that. Or what do you want to optimize? I want to optimize profitability. Then tell me the profit. Okay. Also, what do you use to make those heavy light saws? Oh, no, don't tell me what you use. Where's your bottleneck? The bottleneck? Oh, how much do you always run out of first? Oh, bottleneck. Yeah, The machining department, assembly department, we always have trouble with that when we come to these table saws. There's where our problem is. There's where our bottleneck is. The other doesn't matter. We have plenty of other resources. Those are the big ones. Okay, fine. How many hours do you have dedicated to those? 4,000, 5,000. Good, okay. And if you walk away without these numbers, can you solve the problem? No. So you have to ask them, okay, how many hours does it take in the machine department to do one heavy saw? I don't know. Well, how many heavy saws can you make in 20 hours? Oh, I can make 10 of them. Okay, so it's about 2 hours per saw. Yeah, that's about right. So you have to ask the right question to get to the right numbers. Anyway, go on and on. The other thing is that once you have the structure, it's easy to add other constraints beyond the problem. Here's a marketing constraint, a maximum market demand, like a saturation point of the market. What may be from the marketing department, or from the accounting department, or from the finance department, human resource department, or even from the janitorial staff. I don't know, from the maximum storage you have. But the point is, you can add other constraints from other disciplines once you have that structure. Okay, so there's my soapbox. Let's go on. I'm not going to solve this thing. I've already done this. By the way, product mix means a mix of these products. How much of each? What's the mix between the products? That's what a product mix means. So I define my decision variables, first thing you do. I define my objective functioning constraint set, non-negativity constraints. Got it? I put that into Excel, I solve it. Got it? And I have 1,000 heavy saws, 2,000 light saws for a maximum of $2.1 million. So there's the maximum profitability I can have. Okay? Very good. Now, what about the machining and assembly department? Well, you can say here, oh yeah, you've maxed out. Oh, are those slack or surplus? Good question. This is less than, so those are slack. The slack is 0, so you say machining and assembly are binding. And if you tell that to a client, the response I would get back is, huh? Do what? They go, oh, how would you interpret that? You don't say it's binding. You say, oh, well, if you make 1,000 heavy and 2,000 light, your machining and assembly department are 100% utilized. There's absolutely no hours remaining in those departments. Those departments are 100% utilized. Okay? And then you say your saturation market that you've given me, say there's a maximum of 3,500 saws market. You have 500. Now, is that a slack or surplus? It's less than, so it's a slack. But what does that mean? Well, that means the amount of saws that you're producing is 500 less than the actual market could hold. Okay? And so you say, oh, you mean if you can make more saws, you can sell them and make more money? Yeah, that's what that means. Oh, okay, well, let's do that. Well, you're going to need more machining hours and assembly hours. And the client goes, okay, fine. Here's 100 more hours. And so I want to give them to my manager, give them to you. Here's 100 hours, put them anywhere you want. But put them in machining and assembly because I want to increase this 2.1 million. Okay, where do you put it? Do you put it all in machining and make this 4,100? Do you put it all in assembly, 5,100? Do you put it 50-50, 60-40, 20-80? Where do you put it? Well, why do you put it? I want to put it to maximize my profitability. So you have extra resources that you want to add to this problem to optimize your marginal profit. So this is referred to as a marginal analysis. Where do you put it to maximize your marginal profit? Here's where shadow prices come in. Shadow prices, because this is the value of extra resources. Okay? This is the value of your products. This is the dollar value of your products. These are the dollar value of 1 unit of your resources. In other words, if machining goes up 4,001 hours, then this 400 says your profit is going up by $400. For each unit, for each hour that goes up, then your profit is going up $400 because you're shifting your production mix. Assembly has a $100 shadow price or marginal shadow price profit. Sometimes it's called dual price. Okay, so where would you put all your hours? You put it all in machining because you have 4 times more return, marginal return, by putting it in machining. So, real quick, here's an example of one consultant coming in who does not know linear programming. Says, oh, don't worry about it. I'll put it in assembly. I guarantee you will make more money. Oh, good. I'll take that 100 hours, I'll put it in assembly, and I'll make you $100 per hour more. Well, what's 100 times 100? There's 3, 4, was that $10,000 more? Oh, okay. Well, thank you very much. That's great. That's fantastic. That's awesome. Okay, then consultant B comes in and says, okay, well, you made $10,000 on that, but I can take the same operations, the same people, the same everything, the same time, same everything. But I'm going to take those hours and put it in machining instead of assembly. Everything else is the same. I make 4 times more profit. And that's good business. And that's smart, responsible operations. Someone who knows what they're doing. Okay, so where do these shadow prices come from? They come from Excel. Okay, I'll bring Excel back up here real quick. Okay, and so I'll use it with this. Okay, we've lost time, so I don't want to take too much time with this. But let me minimize this a little bit. Bring this over here. Let's see, I guess I could put, I'm going to put these in here. 900 and then 600. And this is 2, 1, 2, and 1. Okay. And then let me solve this thing. And I hope it comes out to be, it doesn't. Let's see what I do. What did I do wrong here? Oh, this needs to come up to here. I have the other one in there. Solve this thing again. Up. Let me get rid of this. Solve this thing again. Still didn't do it. Let's see what I do wrong here. Oh, sorry about that. Okay, this. I gotta change these things. It was solving what I gave it. It was solving what I gave it. I just gave it the wrong numbers. Okay, now let's do it. There it is, 2100. Now when I solve this, okay, so I solved this. Now when I solve it again, solve it, solve. Here's where the sensitivity analysis comes in. I'm going to click sensitivity. Now when I say OK, it's going to keep the solution, but it's going to create another spreadsheet here of my sensitivity. I say OK, boom, sensitivity report. I open it up, and here's where I have my shadow prices right there. Bing, bing. We won't do that too much in the quiz. You can do it in the homework. You could do it in the memo if you wanted to. But since this is not a linear programming course, it's part of operations, you can use it, but it's not going to be part of a homework assignment. But you can use it if you want to. It is helpful. Okay. It is very valuable in practice. Okay, but this is just an introduction to this material. Okay, pretty clever, huh? So therefore, the shadow prices talks about marginal profitability and marginal analysis. Okay, now let's go to ingredient mix. A cattle feedlot company cattle feedlot operation mechanically blends ingredients to generate low-cost feeds for its cattle that meet daily nutritional requirements. Two principal ingredients are corn and oats. From the information below, how many pounds of corn and oats should be fed to each head of cattle per day to minimize cost? Now, not too many years ago, there was a problem in Colorado with the ranchers with this. The price went down. The feed was high, and they kept feeding their cattle because they say the price was going to come up, because if not, they sold the cattle, they'd lose all this money. They're waiting for the price to come up so they wouldn't lose all their money. So they're waiting for this, and so what's the cheapest way they could do this to wait for the price to come up? So this is a very big issue for ranchers in Colorado. Anyway, so the idea here is now the structure. Up here are the ingredients. Over here are some objectives. These are the requirements of those objectives. And down here is cost. Now, these ingredients are going into a product. These are the cost of the ingredients going into a product. Corn and oats going into a product. So before we were producing a product, tables and chairs. But now we're talking about the cost of ingredients going into a product. Now that product has certain objectives over here, and those objectives then have requirements. And here are the standards. How many minerals of your objective for each unit of corn, like each pound of corn? Calories, vitamins, okay? And we define this by defining, we formulate this by defining our decision variables. We minimize our cost, but this time, these are our minimum daily requirements. So 5, 8, and 4, that's on the right-hand side over here, right? But then for every pound of corn and oats, here's how many minerals, calories, and vitamins we're going to actually put into this product of feed. So it's 100 times C, 300 C, 200 C, 200, 200, 100. But it's greater than, because we want to be more than the minimum daily requirements. So this is a greater than constraint because we are minimizing the cost. So when we solve this problem, we're minimizing the cost, but making sure we have at least the minimum daily requirements. And so essentially we're finding the minimum amount, to put into this product, the minimum cost, the minimum amount to achieve our goals. Okay, so we solve this thing, and we have 15 pounds of corn, 17.5 pounds of oats, with a minimum of $2.65 per head, and that's as cheap as we can get. Okay, and so $2.65 a head, and that you have this many head of cattle, $2.65 a head. There's your cost. That's the cheapest way you can get out of this and get through it. So you have responsible management. Well, if you multiply this through down here, minerals and calories and vitamins, and notice this is greater than, right? So therefore these are surplus. The surplus here, well, minerals and calories are binding. Vitamins have a surplus. Okay, what does this mean? What this means is that calories, now remember this is minimum daily requirements. So the calories and minerals meet the requirements right at the minimum. But the vitamins are greater than the minimum. So you have more vitamins than the minimum. Okay, but that's the minimum cost. That's the cheapest way to do it. Now in this one, notice the shadow prices are negative. Oops. The shadow prices are negative. Again, I use this as an introduction to a linear programming course. Actually, that'd be nice to have a course on operations just in linear programming, goal programming, integer programming. We should, because it's helpful in business. But it's negative because we have a minimum objective function and greater than, and so if the right-hand side increases, then the objective function, it's a minimum, it's going to go up, and you have negative shadow prices. And so the interpretation then will apply to a minimum and greater than. And down here below, I will interpret the shadow prices more. We won't get into shutout prices in this course unless you want to. The third one, the last one we do tonight, is the transportation LP. A company distributes computers from 2 warehouses to 3 customer sites. How many computers are shipped to minimize cost and meet requirements? Okay, down here's the setup. Suppose we have 2 warehouses, Denver, Colorado, and Atlanta, Georgia. We have 3 customer sites, Seattle, Washington, Albany, New York, and Dallas-Fort Worth area. Okay, now Denver here, A, has 1,000 computers to be shipped. Up here, 1,000 computers to be shipped. And B has 2,000. Down here, Atlanta has 2,000. Now, it has to ship these to 3 customer sites. 2 warehouses, 3 customer sites. It's logistics. Now, the 15 here, if you ship, say, a large, like 100 computers from A to 1, it costs $15 per computer on the average. In other words, from A to 1. If like 100 computers were shipped from Denver to Seattle, on the average, it would cost $100 per computer. But if 100 was shipped from B all the way to Seattle, okay, it would be $20 per computer. Okay. But if A ships 100 from all the way to Albany, all the way across the nation, 2/3 of the nation, it would cost from A to 2, it would cost $30 a computer. So these are the unit shipping costs per dollar, per unit, shipping cost per unit that's shipped from a source to a destination. So the question is, how many does A and B ship to 1, 2, and 3? So the customer at least meets its required demand, does not exceed its capacity that it has to ship, and it minimizes its shipping cost. That's called the transportation LP. LP short for linear program. Okay. Well, first of all, let's get the objective function. We define our decision variables. Ij is the number shipped from source I to destination j. So I is A and B, j is 1, 2, and 3. So A1, the cost is 15. A2, the cost is 30. A3 is 20. B1, B2, B3 is 20, 25, and 15. So that right there is our shipping cost. We want to minimize our shipping cost. Okay, so A1, A2, A3, B1, B2, B3, that is how many we're shipping from each source to each destination. Notice there's 6 variables here. It's 6 dimensions. It's not 2 dimensions anymore. It's 6 dimensions. The concepts still apply. Okay, now we create something called capacity constraints and demand constraints. Capacity constraints. Well, everything that A ships cannot exceed its capacity of 1,000. Well, how much is A shipping? Well, A1, A2, and A3, if I add that together, that is everything that A is shipping. That's going to be less than its capacity of 1,000. Everything that B ships is less than its capacity. What about the required demand? Well, everything that customer 1 receives must be at least equal to 500. It could be more, but it has to be at least 500. So A1, B1 then is everything that 1 receives is at least equal to its demand. Likewise for 2 and 3, B2 and B3. Now some people say, well, why would you ship more than you need? You wouldn't. And I could have equality here. But usually you keep these in inequalities because once you have your basic logistic structure, you will add other constraints to it, and sometimes you'll have more demand than you need. Now, there's constraints that are not here down here below. There's constraints that are not here, and that is the non-negativity constraints down here. I didn't put them in, but they are there, and there's 6 of them. All 6 of those decision variables are non-negative, greater than or equal to 0. So I have 6 constraints. Now I can put this in Excel, and I will. next week and show you how to work these. And I have a video. And again, I mentioned it before the break. If you go back to my website, each of these videos show you how to solve each of these problems. And then I have an Excel spreadsheet that you can go through. So I urge each of you to go through these videos, and it explains it, and try it with the going through these videos and work the homework. But the next week I'll do a lecture, if hopefully I don't have glitches again, and I'll work through the homework and show you how it works. Okay, but let me show you the solution. I'll solve it next week. I'm not going to solve it. I'll just I'll show the answer. Okay, here's the setup. I'm taking this table down here and just putting it here. Here's a table. There's the unit costs. Over here's my capacity, and here's my demand. Okay. Now over here is the solution. Now these are the unit costs, but in here these are the actual shipping amounts. These are the values of the decision variables. So A here is shipping 500 computers from A to 1. From Denver to Seattle, shipping 500 computers. Denver is shipping 500 to 2, 500 to Albany, New York. B is shipping 1,000 to 2 and 3. So B is shipping 1,000 to Albany and 1,000 to Dallas. And if you do that, you multiply this, and notice this is 1,000, this is 2,000, 5,000, 1,500, 1,000. If you multiply this times the unit shipping cost, the total cost is $62,500. So the minimum shipping cost with this shipping schedule is $62.5K. Okay, good, we've solved it. But notice below here, Excel solution number 2. This shipping schedule is not the same as this shipping schedule. This solution is not the same as this solution. As a matter of fact, well, this 500 is the same, but this 500 is gone. This 0 went to 500. This 1,000 went to 1,500 and 500. So it looks like this didn't change, but these 4 did change, one way or the other. The numbers just kind of shifted, either this way or clockwise. Looks like they shifted. What did they shift? One went down, and this 500 went down, and 500 this went up. Looks like that this went down and that went up. I don't know, but this is a different shipping schedule with the same minimum cost. I have two solutions. I have two solutions here with the same optimal value of the objective function. So here I have multiple solutions. So this solution has 2 ways to minimize cost. Now remember, with 2 points of solutions, then every point between those is also a solution. For example, if I take, instead of 500, what if I took 400? And this was, if I only move 400 from here to here. So this is 100, this is 1,400. Okay, and this turns out to be 400, and this is 600. I would still have 625. We can try it. I won't try it now, but we could try it because we're getting late. Instead of 2.5 hours, this is going to be 3 hours. But I lost a half hour in there. I'm really, it's very unfortunate. I know people had to leave, but that's why this is recorded. There'll be 2 videos there. The point is, the transportation LP and logistics is very popular. It's a very common type of problem to have multiple solutions. That's why logistics, you have, if you have an LP, if you have the capability, if you have the analytics, you can almost always have very close, if not optimally, minimum cost in your shipping schedules, if you do it right. Okay, it's more complex than that, but here's a good start. Okay, now down below here, I'm not going to cover this. Down here, I have the dual price shadow prices. I illustrate those. I mentioned them here. I develop it. I also develop the interpretation of the shadow prices. I also develop the reduced cost and also the interpretation. We're not going to do that in this course. It goes beyond this course, more of an analytics course. But that's really all I have for this lecture. And well, let me come back. Let me look at this here to see how do we know that the schedule is the optimal? Good question, Dana. Let's bring back my. We know it's optimal because when I put this in Excel and I solve it, it says an optimal solution was found. So it tells me it was optimal. But also, you can try it too. In other words, this is optimal. Okay, and so, well, I probably should do this. You know, I really should do this. I want to hurry and get at it. I want to finish this. I feel bad about being so long, but let me open this Excel file. There it is. Open, open, open. Where are you? Hello? It's thinking about it. And there it is. Here we go, enable editing. And I think I have it here. Let's come into data and solver, make sure it's there. Yep, there it is. There she blows. Okay, and it's already there. Let me close this out. Now notice we also knew that there was another solution where if this was 500 and this is 1,000, it's still 625, see? Now, we know that this is optimal because right here, if I make this, suppose I moved it this way. In other words, this was 600 and this is 400. This is no longer 625. Okay. Oh, it went below because I violated this. I have to go the other way. 400 and 600 and then 900 or 1400. 900. Okay, I still have to meet my requirements here. I can't go over here, can't go over here. I went below here, and it's going to go down. So I bring this back to 500, 500, and 50, and 1,000. There we go. But also, if I solve this thing, let me solve it again. Solve it. And right here it says, solver found a solution. All constraints and optimistic conditions are satisfied. If I do a sensitivity analysis, let me go ahead and do this and say, okay, it'll do a sensitivity report. And there it is. Okay. And it'll give me my shadow prices here, 400 to 100. Oh, that's not the same one. Let me close out of this. Oh, don't want to do that. Do not want to do that. Sheet 1. It brought up the other one. There it is. That's sensitivity report with this one. So there's my shadow prices for all of the less than constraints and greater than constraints. Notice you have a -5 for shadow price for the -4 or greater than constraints. Again, it goes beyond this course, but there's my shadow prices. That's how I know it's optimal. Okay. Well, this working through this stuff, it has been had problems. We've gotten through it. I really appreciate you sticking with me. And that's, again, I'm so glad that years ago I generated these videos. Now, you're going to have this video. It's going to be 2 hours long. 6:30, 7:30, 8. It's going to be 3 hours long. I doubt if anyone's going to watch all of this. There's going to be 2 of them. You can go back and forth. But these videos, though, an introduction, these videos and product mix and everything, these are not that long. So if you this is going to be 9 minutes, Okay, this is going to be 5.5 or 6 minutes. This is the LP. Whoops, this is the the transportation. That's 13 minutes. So that's, what, 35, 40 minutes instead of 3 hours. But anyway, I don't stop talking about that. It happened. What can you do? It happened. Things like that do happen, and we got through it, didn't we? Well, that's all I have for tonight. And I have helps out there to do the homework. I'm going to post the homework. I'm going to post the quiz, the homework, and memo probably by tomorrow, and work on it. And the next week, the video or the lecture will be working through the homework. We're working through the quiz and the homework and memo 1 that was part of forecasting. That's what I'll do next week. So we got through this, and we did that. We did that at the very beginning. The quiz question 6. There was confusion in there. I want to go back right after this and just give everyone that question. I think you see the answers in there, and sometimes people answered it because, we answered. People answered it, and it was confusing. And hopefully, people can see the answer and understand the answer. If not, you can ask it next week before, during office hours. But if you just look at I'll give everyone credit for that because it was confusing. I mean, I had the problem that I answered it wrong, then right, then wrong, then put this, put there. People were asking different things, and that was unfortunate. So I'll just change the grade on that one because those things do happen. So we got through this, and hey, everyone, stick with me. A lot of people stuck with me to the end. Wow, that's good, strong people who want to learn this stuff. It's good stuff, and I think next week, as we start working through the problems being more applied, we will be hopefully you'll see exactly how this stuff works through the homework. And you see the homework, the quiz and the homework. The quiz is mechanics, but the homework is applications, some good applications. And so we talked a lot about some of the definitions and terms and relationships and how to solve it with Excel. Next week is when we start applying it. So that's when we are going to start learning a linear program much better when you see the application. The quiz was that quiz was tough. Okay, that quiz was tough. Well, I appreciate that, and that's why I have a video to work through it with you. Okay, and also I encourage people to talk to each other with a discussion board on Canvas. Share your answers, share your Excel spreadsheets, and do back and forth or whatever you want to do it. But collaborate as much as you can or as much as you want. And this is 6630. Well, again, 2010. I work all the homeworks on all of them. So that's all I have for this lecture. I'll quit talking here. It's been 3 hours and with glitches here and there, but again, we made it through. That's all I have for tonight. And I'll see you at office hours Wednesday and Friday at 7 p.m. on Zoom. Next week with the lecture with live stream, I will be looking at the application of linear programming. That's all I have for tonight. So between now and the next time I see you, be careful, be safe, and take care.